Hi, everybody. All right, so there's a bunch of moving parts to the inorganic carbon cycle. Well, let's see how this plays out. Once you sort of get a handle on the steps, then hopefully it makes a little more sense. Uh, First and foremost, right, the inorganic carbon cycle is how carbon cycles around a planet uh, by chemistry and geology. A planet needs to be geologically active in order to keep the carbon cycle going. So, which kind of planet is more likely to have long-term active geology? Well, a large planet, like I said in the video lecture, a large planet takes more time to cool off. So the planet is going to stay hot and geologically active for a longer period of time until it eventually cools off. A small planet can be geologically active. It can be hot, and the magma inside the planet can be convecting, and the volcanoes can be active. But if the planet is smaller, it's going to take less time to cool off. So the small planet will cool off in less time. When the planet cools off, the magma stops convecting, the volcanoes go dead, it stops being geologically active. So if you're looking for a planet that is going to be hot and geologically active for a longer period of time, you need a larger planet. Something more like Earth and less like Mercury. Okay. So how does the carbon cycle around the planet? Like it says on the next page, right? Write the letter. We start off on the next page. We start off with carbon dioxide in the atmosphere at A. And then happens is the carbon dioxide mixes with water vapor in the atmosphere, and when the water vapor condenses as clouds, the carbon dioxide is dissolved in the water as the carbonic acid. And then the rain falls, the carbonic acid falls in the raindrops, and that's how the carbon gets removed from the atmosphere, by getting scrubbed out of the atmosphere through rain. And the rain, well, it either falls right into the ocean or it falls on the land. The carbonic acid, it's a weak acid, and so the carbonic acid reacts with minerals in the rocks, and it forms that bicarbonate. And so then the bicarbonate flows through the rivers into the ocean. And then when the river water flows into the ocean, the bicarbonate goes with it. And now the bicarbonate is floating around in the ocean water, where it will react to the calcium in the ocean water, right? There's calcium dissolved in ocean water. The calcium in the ocean water reacts to the carbonate to form calcium carbonate, and calcium carbonate is the kind of mineral that limestone is formed out of. And so this calcium carbonate settles from the top of the ocean, it sinks to the bottom of the ocean, and it builds up layer by layer by layer sediment. The layers of calcium carbonate sediment build up and build up and build up at the bottom of the ocean as rocks, as sedimentary rocks. And that sedimentary rock is stuck. It's stuck there as rock, and the carbon is stuck there as rock at the bottom of the ocean until eventually plate tectonics will drive that rock back into the mantle of the Earth. This pencil is hard to see on this color here, but that limestone, that calcium carbonate rock, eventually gets subducted back into the mantle, where it gets heated up by the magma of the mantle, and when that calcium carbonate rock gets heated up, it melts, and the carbon dioxide gets unlocked from the rock so that bubbles of that carbon dioxide can come up through the volcano, vent out of the volcano, and go back to the atmosphere where it started, and the cycle is complete. Right? All the time, the volcanoes are erupting, putting carbon dioxide in the atmosphere. The carbon dioxide is being removed by rain, flowing through rivers into the ocean, settling from the ocean into the ocean floor, and then slowly getting driven back down into the mantle to be melted and released out of volcanoes back into the atmosphere. That's why we say we need active geology on this planet. You need plate tectonics. You need plate tectonics to carry the carbonate back into the mantle. You need a hot mantle. You need hot magma to melt the rock and let the carbon dioxide out so that it can blow out of volcanoes back into the atmosphere. Right? Without plate tectonics or a hot mantle and volcanoes, you can't keep the carbon cycling from the atmosphere to the oceans to the ground and then back. So, what process releases the carbon dioxide into the atmosphere? It blows out of volcanoes. What process removes the carbon dioxide from the atmosphere? Well, it's removed from the atmosphere by rain, by being dissolved in raindrops. Which step is the slowest? Well, volcanoes erupting, when volcanoes erupt, they erupt pretty fast. Rain falls pretty fast. It takes a while. It takes a while for the calcium carbonate to sediment and build up at the bottom of the ocean. But that's not the slowest. The slowest step, once the carbonate is locked up as rock, it takes a very long time. Tens of millions, hundreds of millions of years to be slowly subducted back down into the mantle. And then once this rock reaches the mantle, it gets melted, the carbon dioxide gets released, it vents out of volcanoes back to the atmosphere. So the sedimentation of the carbonate from the top of the ocean to the bottom of the ocean is slow. But the slowest step is plate tectonics. It's the subduction to turn the rock back into CO2 gas. So which step is the slowest? I'll say subduction. Right, the plate tectonics. You can phrase that any way you want to, but it's the right idea. Okay. I'm running out of room for myself here, but, okay. And one of the reasons why, like it's getting at here, one of the reasons why the Earth is such a nice and temperate place to live is that the Earth has this thermostat where, like it says here, suppose the amount of CO2 in the atmosphere is too high. So if there's too much CO2 in the atmosphere, that's going to make the greenhouse effect stronger. And if the greenhouse effect is stronger, then the temperature of the planet will heat up. But if the temperature heats up, then there's going to be more evaporation. More evaporation. If there's more evaporation off the oceans, then there's going to be more rain, right? If there's more water vapor in the atmosphere, then the atmosphere is going to be more humid, and more of that water vapor can condense as rain. So I'm going to say the amount of rain will increase. But if there's more rain, then that's going to be, the rain is going to scrub more CO2 out of the atmosphere. So the amount of CO2 is going to decrease. And if the CO2 decreases, if the amount of CO2 in the atmosphere decreases, then the greenhouse effect will get weaker and the temperature will go back down. That's what I mean when I say thermostat, right? If in 1 year, let's say, in 1 year, more volcanoes erupt than usual. And so that pumps more CO2 into the atmosphere, The Earth warms up, there's more evaporation, which drives more rain. The rain scrubs the CO2 out of the atmosphere, so the temperature cools back down. Right? Just like the thermostat in your house, right? If it's too hot, then the air conditioning kicks on and it lowers the temperature to keep the temperature stable. Or let's say in a year, fewer volcanoes erupt, so there's less carbon dioxide in the atmosphere. Well, if there's less carbon dioxide in the atmosphere, then the greenhouse effect gets weaker and the temperature will decrease, which means less evaporation. If the world is cooler, then the amount of water evaporating off the oceans will decrease, which means there's now less humidity, there's less water vapor in the atmosphere. If there's less water vapor in the atmosphere, then there's going to be less rain. If there's less rain, then it's not going to scrub as much CO2 out of the atmosphere. If there's less CO2 being removed from the atmosphere, then that gives the volcanoes a chance to put more CO2 in the atmosphere, so that'll raise the level of CO2. And if there's more CO2 in the atmosphere, the greenhouse effect will get stronger and the temperature will go up. So if there's not enough CO2 and the world gets colder, then there's less evaporation and less storms. So the CO2 goes up, the temperature warms up again. So that's one of the reasons why the Earth is such a nice and temperate place, is that our planet uses the inorganic carbon cycle to regulate the temperature so that the planet doesn't get too hot or too cold. If the world warms up, then there will be more rain and storms, which will remove CO2 from the atmosphere so things cool off. Or if the Earth cools off, then there will be less evaporation and storms, which lets the CO2 go back up and the planet warms up again. Either way, if the planet cools off, it can warm up. If the planet's too warm, it can cool off, and it keeps the temperature on Earth nice and stable and temperate. Not too hot, not too cold, just right for us to live. But in order to do that, in order to take advantage of this thermostat, we have to have rain. We have to have liquid water to evaporate. We need water vapor to condense as rain to either remove more or less CO2 from the atmosphere. And we need volcanoes. We need volcanoes to either put the CO2 in the atmosphere, if there's too much, or to add a little more CO2 in the atmosphere in case there's not enough, in order to keep it all going. We need, to keep the inorganic carbon cycle going, we need volcanic activity. We need rain. We need oceans. We need plate tectonics. And so that's why Earth has a successful inorganic carbon cycle today, is that the Earth has plate tectonics and volcanoes and rain and oceans. And so the Earth can keep this all going, not just to regulate the CO2, but to also regulate the temperature. What about on a planet that doesn't have a successful inorganic carbon cycle? So say Venus, right? Venus used to have a successful inorganic carbon cycle. Venus used to have this thermostat keeping the temperature more stable. But from all the evidence of volcanoes and geology, it looks like about 750 million years ago, there was just a massive amount of volcanic activity on Venus. And so all those volcanoes erupting put way too much CO2 in the atmosphere. So then the planet got warmer, right? What happened to the planet's temperature? Well, with all that extra CO2, the greenhouse effect got a lot stronger, and the planet warmed up. If the planet warmed up, then what happened to the ice caps? Well, if the planet gets warmer, then the ice caps are going to melt. If all the water vapor, so all of the liquid water and the ice caps warm up, that's going to evaporate the water. And so then the amount of water vapor in the atmosphere increases. If there's a lot more water vapor in the atmosphere, then the rain and the storms are going to get stronger, and therefore, what happens to the water level? Well, the water level is going to increase, right? Because you've got the ice caps on the poles melting, turning into liquid water, and you've got all this rain pouring down, turning into liquid water, and so for a little while, the warming of the planet made the ocean levels rise. And if it stopped there, then things wouldn't be so bad. But it didn't stop there, right? The ice melted. The rain kept pouring down, and the ocean levels got higher and higher, but eventually there was so much CO2 put into the atmosphere that the temperature got hotter and hotter and hotter. Well, in order for water to turn into rain, it needs to be able to cool off. You need water vapor in the atmosphere to cool off, condense as raindrops, and then fall as rain, because when the rain falls, it removes the CO2 from the atmosphere. Because there were so many volcanoes on Venus erupting so fast, the planet got warmer and warmer and warmer, until eventually the water vapor in the atmosphere couldn't rain out anymore. It all stayed as water vapor in the atmosphere. And if you remember back from the greenhouse effect microtask, water vapor and carbon dioxide are both, right? So you're getting this increase in water vapor in the atmosphere, you're getting all the CO2 from the volcanoes, and water vapor and CO2 are both really strong greenhouse gases. So the amount of greenhouse gas in the atmosphere built up and built up and built up, both the water vapor and the CO2, and therefore the temperature of the planet got hotter and hotter and hotter. The temperature got hotter, and it couldn't cool itself off. Because how does a planet cool itself off? Well, let the water evaporate and let it fall as rain in order to cool off the planet. Let the rain fall, let that scrub the CO2 out of the atmosphere, and the planet will cool itself off. But Venus couldn't do that, right? Because Venus had so much CO2 dumped into the atmosphere from all these volcanoes erupting, once the rain stopped falling, the volcanoes kept on adding CO2 to the atmosphere, and it had no way to get out. So that's what a runaway greenhouse effect is. A runaway greenhouse effect, right? The greenhouse effect is where greenhouse gases, specifically carbon dioxide and water vapor, build up in the atmosphere, make the planet hotter, and it can't cool itself off. Because the rain can't fall anymore. The water vapor is too hot. Here on Earth, we have a greenhouse effect, but the CO2 in the atmosphere does still have a chance to get scrubbed out by the rain. And Venus used to have that for a while, until there was too much CO2, the planet heated up too much, and it had no way to cool itself off anymore. It broke the thermostat, and the planet got hot and stayed hotter. Mars also used to have all the right ingredients for a runaway greenhouse effect, right? When you look at Mars today, there's dormant volcanoes. There are signs that a very long time ago there were large bodies of liquid water on Mars. How did the liquid water get there? Well, probably from the rain. So Mars used to have the ingredients for an inorganic carbon cycle. But Mars is too small. Mars is a third the size of Earth. Well, it's a third the mass of Earth. It's more like half the size of Earth. It cooled off in less time. When Mars cooled off, the volcanoes stopped erupting. And if the volcanoes stopped erupting, the planet didn't freeze immediately, right? But if the volcanoes stopped erupting, then this can't happen anymore. If the volcanoes stopped erupting, then the carbon dioxide that was in the atmosphere got scrubbed out of the rain, put into the oceans. It built up at the ocean floor as carbonate rocks, and it was stuck there. Because when the volcanoes stopped erupting, any plate tectonics also stopped, right? Plate tectonics and volcanism are both powered by heat. So when Mars cooled off and the magma stopped convecting, this stopped and this stopped, which means all of the carbon went from the atmosphere onto the ocean floor as rock, and it got stuck. So what did that happen? Well, as the CO2 got removed by the rain, the temperature would cool off. If the temperature would cool off, then the planet got colder, and therefore the water could freeze at the ice caps. What happened to the amount of water vapor? Well, it all rained out, right? Either the water vapor rained out of the atmosphere or it froze on the ice caps. If there's less water vapor in the atmosphere, then there's going to be less rain and storms. If there's less rain and storms, the ocean level will decrease, right? The water from the oceans the water from the oceans is either sinking into the ground or freezing at the poles. And so the water levels went down, down, down. Eventually the planet got so cold that the water couldn't evaporate anymore. And you've broken the thermostat again. When all the water vapor in the atmosphere froze as snow, then the greenhouse effect collapsed. Right? Remember, what are the two main greenhouse gases in the atmosphere? Carbon dioxide and water vapor. And when all that carbon dioxide and the water vapor rained out and froze on the surface, the atmosphere got thinner. The atmosphere was thinner with less greenhouse gases. So if there are less greenhouse gases in the atmosphere, you're going to have a weaker greenhouse effect, and the planet gets even colder and it freezes. That's a runaway refrigerator, right? A runaway greenhouse effect is where the planet gets too hot and it can't cool itself off. The planet gets too hot, and when the rain stops, then it can't cool itself off. On Mars, the planet got too cold. The planet got too cold. All the rain fell. All the rain fell out of the atmosphere, or froze out of the atmosphere, which means, and then there were no volcanoes erupting to add more carbon dioxide in the atmosphere, so the planet couldn't warm itself up. Right? Once all the rain and all the CO2, well, not all the CO2, Mars still has some CO2 in the atmosphere, but less. Mars's atmosphere is very thin these days. But once all the rain fell out and all the CO2 that could be scrubbed out of the atmosphere the greenhouse effect failed, the planet couldn't warm itself up again, and it stayed frozen. That's why it's called a runaway refrigerator. Mars got too cold, and it had no way to warm itself back up. Burning fossil fuels, right? The hydrocarbon, the combustion of hydrocarbons that we were talking about in the greenhouse effect microtask, right? Burning fossil fuels puts more carbon dioxide in the atmosphere. If we burn too much fossil fuels too fast and we add too much CO2 into the atmosphere, it's going to be like what happened on Venus, where all the CO2 got released from too many volcanoes erupting. And so if we add too much CO2 into the atmosphere, faster than the rain has a chance to remove it, right? If we add too much CO2, if we're burning coal and oil and natural gas, if we're burning all these hydrocarbons and adding CO2 in the atmosphere faster than the rain can remove it, then the Earth will warm up and get too hot, and it won't be able to cool itself down, and that'll be a runaway greenhouse effect, like what already happened on Venus. That's why we're so concerned about global warming, climate change, the greenhouse effect, and burning fossil fuels today is that we know what happens. We know what happens when a planet gets too much carbon dioxide in the atmosphere. Venus happens. The planet gets hot and it can't cool itself off anymore. Right now, the Earth has this functioning thermostat where if it gets too warm, then the rain can fall, remove the CO2 from the atmosphere, and the temperature goes back to normal. Eventually, though, if we keep adding too much carbon dioxide, eventually the planet could get so warm that the rain stops falling. And if the rain stops falling, we break this cycle. We break all of this, and the planet can't cool itself down anymore. It's not a speculation. We know what happens when a planet has too much CO2 too fast. You get a runaway greenhouse effect. It happened on Venus, and if we don't stop burning fossil fuels and keep on adding CO2 to the atmosphere faster than the rain can remove it, then the same thing will happen on Earth as it happened on Venus. That's why all the discussion about fighting global warming and climate change focuses on stop burning fossil fuels. Stop making the greenhouse effect stronger than it can regulate itself. Okay. Right. It's like I said in the lecture video. Venus, Earth, and Mars all started out very similar. Venus, Earth, and Mars all started out hot. They started out volcanically active. There's evidence that water used to exist on all three planets. So there was a functioning carbon dioxide cycle on Venus, Earth, and Mars. But the volcanoes erupted too much, the rain stopped, and when this part of the cycle stopped, all the carbon dioxide stayed in the atmosphere and it had no way to get out. On Mars, the geology stopped and the carbon dioxide ended up as rocks in the ground and got stuck there. A little change here and a little change there, right? Venus, Earth, and Mars started out very similar, but you change one little thing. You either have too many volcanoes erupt, or the volcanoes stop erupting. And once you break the inorganic carbon cycle, then you break this thermostat, and the planet either, roasts in the case of Venus, or it freezes in the case of Mars. And the Earth, 4.5 billion years later, the Earth is still the nice place to live that it is because we still have a carbon cycle that functions. Okay. I hope that simplifies things, right? There's a lot of moving parts here, but hopefully we've broken it down so that it's making a little more sense. If you've got questions, come on into office hours and we can talk it through, or post a question to the discussion board. All right. Have a good one, everybody.